Hi, everybody. Welcome. My name's Jordan Young. I'm a manager of analytics engineering at Glue Mobile. And I'm going to talk a little bit today about our data platform and how we use Kinesis and Apache Storm to handle what is fairly large data load every single day. To start, who here has used Amazon Kinesis at all or is familiar with it? Okay. What about Apache Storm? And what about Hadoop? Okay, cool. So let's get started then. Let's go over what we're going to talk about. I'm going to briefly introduce Glue Mobile, some of our data requirements and challenges. And then I'm going to talk a little bit about our architecture and some of the decisions that we've made. I'll try to be brief there. I'm just going to try to set some context. And then I'm going to go fairly deep into Kinesis, and especially the Amazon Kinesis connector library, how that works and how it's been a good solution for us. Then I'm going to spend some time going through our real-time implementation, which uses Apache Storm, and how we've been able to integrate Kinesis with that. And then lastly, I'm going to go through kind of a bunch of kind of ad hoc challenges and insights that we faced building out this platform, things that I wish we'd kind of known about before, but that we've had to learn through trial and error. All right, so Glue Mobile is a leading publisher of mobile games. These are a few of our franchises. Our best performing game is Kim Kardashian Hollywood. But we have a couple other fairly recognizable franchises, Deer Hunter, Contract Killer, Racing Rivals, and so forth. Right now we have 4 titles in the top 100 grossing. Typically like 4 to 6 million daily active users. And since we started collecting data back in 2010, we've had over 1 billion global installs. So what do we collect? Those 4 to 6 million daily active users generate quite a bit of data, anywhere between 700 million to, we've had a few days where we've gone over 2 billion events per day, 600 bytes an event. That means we could theoretically collect up to 1.2 terabytes in a single day. And if we had a successful game launch, for example, we need to be prepared to scale up higher than that. And where do we get this data? So the vast majority of it comes from client-side SDKs. We also collect data from game servers, from central services servers, from an attribution partner, from ad networks, from third parties, and so forth. All right, so some of the basic requirements around it. We need near zero data loss, high levels of uptime. We need to be able to handle a flexible data format. The kind of data that we collect for Kim Kardashian Hollywood is not necessarily going to be the same kind of data that we collect for Contract Killer Sniper. Those are 2 very different games with 2 very different engines. And so we need to be able to pass arbitrary fields in if we want to be able to do good analytics on it. We also need to be able to do real-time aggregations. And we need reasonably low latency for ad hoc queries. So it can wait till the next hour typically for that sort of thing. Something like how much money we've made can't, but something like getting the tutorial completion rate or whatever, something that we haven't instrumented previously can wait till the next hour typically. And then some other requirements, it can't be expensive. It needs to be implemented with minimal engineering effort. Through most of this process, I've been the only engineer working on this. With a little bit of help from some contractors. But we definitely needed something that was going to be easy to maintain and simple to set up. And then also we needed something that would require minimal changes to existing games. So we couldn't just go tell all of our client teams, oh yeah, you have to totally restructure the way that your game works and you have to use the server to send data. That was never going to work. We pretty much knew that we had to just build an SDK that they could drop into their game. All right. So where does that leave us? So about 3.5 years ago, well before I started at Glue, our data platform was every game had a separate SQL Server shard. They all had inconsistent schemas, and that was a complete disaster. It would be like a whole day of work to compare the retention numbers between 2 games. It did not work at all. And so they decided to go to a third party. And that worked a lot better. We were able to compare retention numbers across different games, for example. But ultimately lacked the flexibility that we needed in our data platform. So we talked to our third party, and we had them set up a raw data API where we could pull all of our data every hour over HTTP. So we wrote a Python application that would pull all that data over HTTP and upload it to S3. Then we set up a Hadoop cluster and used that Hadoop cluster to calculate all the aggregates that we were interested in looking at in dashboards, as well as to do all of our ad hoc analysis. And then we used Amazon Redshift as the backend for a bunch of Tableau dashboards. And so we were able to set this up fairly quickly. And it worked reasonably well. Mostly, these are components that were ready-made and so forth. But we eventually ran into some problems. So that strategy of downloading all those files over HTTP was not particularly reliable. If you can imagine, you're pulling down terabytes of data a day. You're gonna run into some situations where you don't get complete files and so forth. It also didn't necessarily scale well. That third party didn't necessarily know when we were gonna, didn't necessarily scale up in advance of some of our large launches, and so we'd have downtime right during a game launch, which was a total disaster. And it wasn't timely. We had to wait a few hours before we could pull that data down. And so something like real time was not really an option. All right, so where did that leave us? Well, we had to bring our data collection in-house. So that meant building our own analytics SDK, and it meant setting up a framework for collecting data from that SDK. And so we had two basic options here. We could use something like Kafka, build our own service, or we could use a hosted service like Kinesis. And given that I'm here, you can probably guess which one we chose. All right, so really briefly, before I get into our particular implementation of Kinesis, let's go over the basics of it. You have producers which generate data. That could be a server, a mobile client, whatever. It puts it onto a Kinesis stream. That stream is defined by shards. So a stream could be anywhere from 1 to theoretically an infinite number of shards. Those shards have capacity limits, so the more data you want to pass through, the more shards you need. And then you have consumers that read data off the stream. And sort of the fundamental difference here between something like Kinesis and SQS is you can actually have multiple consumers reading the same stream of data because it uses checkpointing instead of deleting records. All right. And so why did we pick Kinesis? Minimal setup time, all these pre-built applications, which are pretty useful. The Kinesis connector library and the Kinesis storm spout worked really well with the architecture that we were sort of planning. No maintenance, no hardware, which meant with one engineer you could actually run this. And there wasn't really a price consideration. It wasn't a big enough difference to factor into our decision. All right, so our producers. Like I said, we had to build client SDKs. We built a native Android plugin in Java, and we built a native iOS plugin in Objective-C. And we built a Unity wrapper for our Unity titles. We built these on top of the AWS SDKs for their respective platforms. And these SDKs, these plugins, implement our own internal analytics schema. So we don't have to worry about a client team sending us records that don't conform to our schema. They have to conform to our schema. And then we also have additional server-side implementations like I discussed before. We don't do any record batching or any compression, which might seem like not a smart thing to do, but it turns out the cost difference is minimal enough that we don't care, and it makes working with some of these downstream applications a little bit easier. We flush records every 30 seconds or upon certain important events. We do our client authentication using Cognito, and we have IAM roles for our server authentication. All right, so we have these producers generating data. How many shards do we want the stream that they're writing to be? We made an architecture decision to have one global stream for all of our data because it's all being processed by the same system in the back end. We don't really treat the data from multiple games any differently in this sort of perspective. So how big does that stream need to be? Well, there's some limits on your shards. 1,000 records per second, a megabyte per second in writes, 2 megabytes per second in reads. So in our situation, let's say we peak out at 20,000 records per second, 600 bytes per message. So in order to handle the message volume, we'd need at least 20 shards. Those 20 shards are going to cover our write capacity easily, since we only have to do 12 megabytes per second of writing. And that we're going to have 40 megabytes per second of read capacity, which means we could theoretically run up to 3 applications. So 20 shards, right? That's what we should go with. Well, probably not. There's a couple other considerations. So like I said, what is your peak load going to be? Down to the minute. Are you all right accepting any sort of delay? You have to provision for that. It's also probably a good idea to have some excess capacity. I'm going to talk a little bit later about scaling this, and it's totally possible to do, but it's also not completely trivial, and so it's probably better if you just are scaled up, especially if you don't want to be scaling up in the middle of a game launch, for example. That's probably not ideal. And then the last thing that I don't think anyone really thinks about is what happens if your consumer applications, or if your applications that are consuming data off the stream go down for an hour or something like that. You're going to have to catch back up. And if you're right at those read limits, you're not going to be able to do that because you're going to get throttled. So it's helpful to have a little bit of extra space there, just in case your application ends up getting behind. So given that we have 35 shards set up right now, and we have a fairly big game launch at the end of the month, and so we're probably potentially going to think about scaling that up even a little bit further before we do that. All right, so let's go into a little bit of detail about our consumers. So we use the Amazon Kinesis connector library, which is not to be confused with the Kinesis client library. They're both KCLs. It's really confusing. It got me for quite a bit of time. So the Kinesis connector library sits on top of the Kinesis client library. The client library handles stuff like the checkpointing. It uses DynamoDB to do checkpointing. It handles stuff like distributing shards across multiple instances of your application. All you have to do is just give your application, give another instance the same application name, and it'll automatically load balance those shards across it. So if you have 35 shards and 5 applications, or 5 instances of your application, it'll give each of those seven shards, and so forth. What the Kinesis connector library is just a really simple framework for building an application on top of that. And so it follows a basic data flow. You get records from the shard, you transform those records, you filter those records, and then you insert them into a buffer. This buffer has a should flush method. When that's triggered, it takes all of the records that are in the buffer and it emits them somehow. And so in order to get this to work, all that you have to do is implement this pipeline. And so this is actually our exact pipeline. I didn't change any code here or at all. You can see that there's a transformer class that implements that transformer interface, that iTransform interface. You have a filter class that implements the iFilter interface. You have a buffer class that implements the iBuffer interface, and you have an emitter class that implements the iEmitter interface. And I'm going to get into some of the details about our transformer, but really quickly, let's talk about that basic memory buffer. So that's sort of the default that comes in Amazon sample application, and that was adequate for our needs. Basically, it lets you input, or it lets you emit records after a certain amount of time, or a certain number of records, or a certain byte size of the buffer. And so you can implement limits for each of those, and it'll emit after that. And then we're also pretty much using a standard S3 emitter with just a couple changes for file naming and stuff like that. All right, so what might a transformer implementation look like? So we're not really doing a whole lot here. You could do more. The important stuff is that we're adding the sequence number in to the record, and then we're getting the system timestamp. So right now there isn't a way for us to get the timestamp of when a record was added to the stream, which is what we really want. Theoretically, Amazon is going to come out with this, and will let us have access to that data. But for the time being, this is the best thing that we have. We can get the timestamp of when it was actually processed. And if your application is running up to date, that's only going to be off by like 10, 20, 30 milliseconds or something like that. So not a big deal. Anyways, we append that stuff, and then we return the JSON string. And that's all we do. And that's pretty much our entire consumer application. It took very, very little effort to implement it. All right, so let's talk about real-time now. So first, I want to kind of talk about Storm a little bit. So what is it? It's a distributed fault-tolerant framework for processing real-time data. So it views incoming records as tuples, and those tuples are passed through an arbitrary directed acyclic graph of nodes called a topology. And there's two types of nodes. There's spouts, which emit tuples from outside the topology to in the topology, and then there's bolts, which process tuples that are already in the topology. So you have usually like a couple spouts, and then some arbitrary number of bolts that do whatever it is that they want to do. And so the result is you can read from anywhere and you can write to anywhere in real time. Okay, so a little quick bit on some cluster architecture here. You have a Nimbus machine, which is your master node, sort of like a job tracker in a Hadoop cluster, or resource manager, I guess, Yarn. That does stuff like it sends the jar files out to all those supervisor machines, which are your slaves. It assigns tasks to each worker that you've spun up on the supervisors and so forth. That talks to the Zookeeper cluster, which is, in our case, consists of 3 machines, and that handles state. And so this is pretty important. It handles both the state of tuples as they're flowing through the topology. So it knows what bolts have processed what tuples and which ones have been finished processing, and that's important for Storm's reliability model. It uses that to guarantee at least once processing. And it also stores the state of the shards in your stream. So it does all the checkpointing, just like DynamoDB does the checkpointing for any Kinesis client library application. So the Zookeepers are tracking state on these supervisors. Typically, those are going to be large instances. They have some number of workers, which are JVMs. The default is 4. We have reason to think that it's better to use less of those, at least in our use case. And then sitting on each of those workers, you have some arbitrary number of executors, which are threads. And then on each of those executors, you have some arbitrary number of tasks, which are executed serially on those executors. All right, so what does it look like from the topology perspective? So this is a really simple topology that might let you calculate some basic metrics from data coming through Kinesis. So you have your Kinesis Storm Spout that's reading records off Kinesis and sending them into the topology. Then you have a deserializer bolt, which is maybe taking those records and deserializing them into some sort of a class to give you easy access to different fields or whatever. Then you might have a segregator bolt, which takes all of that data and creates a bunch of different data flows, a bunch of different streams that downstream bolts can then subscribe to. So you might have an aggregator that subscribes to your monetization events and calculates your revenue in real time. You might have an aggregator that subscribes to some sort of a heartbeat event and calculates your unique users. You might have a filter that filters out and pulls down QA data or something like that. And in our instance, we're writing it to Amazon RDS MySQL database, but that could be really written to anywhere. That's sort of an arbitrary, well, not an arbitrary decision, but from Storm's perspective, it's arbitrary. All right, so let's talk about implementing this Kinesis Storm Spout. So the kind of first step in getting topology to work. So you have to set up a Kinesis Spout config object. And a couple of these options are fairly important. So like I said earlier, Zookeeper handles all the state. It handles all the checkpointing for the shards in your stream. And all of that state is tied to a zookeeper prefix. So if your topology goes down, you want to launch it again. If you keep the zookeeper prefix the same, it's going to start processing records where it left off. And so, like I said, that's sort of important in terms of guaranteeing at least once processing. If there isn't a prefix that has any sort of state associated with it, it's going to default to that initial position in stream. So you could say you could start processing it from the latest record, or you could start from the trim horizon, which in our case would be 24 hours. Would be 24 hours in the past, and you could sort of imagine situations where you might want to do either one of those. But typically, like, you want to keep some sort of checkpointing, of where your stream is located. How far down each shard has gone. And then the last important thing, and I'll discuss this a little bit later, is that empty records list backoff millis. That has some implications for when you do shard splitting on your stream. Okay. Anyways, you set up that config object. You set up a Kinesis Spout object using that in your credentials, and then all you have to do is builder.setSpout and give it a name so that downstream bolts can refer to it, and then give it some parallelism hint. We found that it's probably a good idea to have one executor per shard that you have. It's not necessarily totally necessary to do that. It'll still function without that, but we found that that's probably a good idea. All right, so given that, like, some basic lessons that we've learned while implementing this. So for starters, only extract necessary fields when you're deserializing. So initially, we extracted every single field, including this big JSON blurb, and that was really slow. It took a ton of hardware to handle our entire stream. When we limited that to only a few fields, it made things a lot faster. We realized, like, if we really needed that data on a small set of events, we could just filter and then pass the record, and then just pull out those fields at a later time when we don't quite have, like, the whole fire hose of data flowing to the stream. We've also found that it's helpful to have big instances with only a few workers. So having too many workers can reduce the throughput quite a bit, but sometimes it's necessary if you want to have some flexibility, especially if you're running multiple topologies on a single cluster. So you might want to be able to break it down into more granular components. And so there's a bit of a trade-off there. And then lastly, like, our final state where we're at with our current topology, so we can handle 42,000 records per second, and that's with 4 C4-2X large instances as our supervisors, and then we're using 2 M3 larges for our zookeepers, and an M3 extra large for our combination Nimbus zookeeper machine. It's pretty typical to have those running on one machine. There's no reason why they can't. Although we're thinking about possibly downsizing those a little bit. But ultimately, it's a pretty fast framework. We're able to handle more than enough data on not really that much hardware. All right, so where does that leave us? So this is our new architecture. So we have our SDKs and server, Kinesis producers, wherever they are. They're sending data to our Kinesis stream, and then that's being read by 2 different applications. So we have the Kinesis Storm Spout, which is sending those records into a storm topology, which is generating real-time aggregates, which we're storing in a MySQL database, and then viewing those with a lightweight front end. And then we also have our batch layer, which we're using that Kinesis connector library application to upload that data to S3. Every hour, we ETL the previous hour's data into a Hadoop cluster, which we store the data there for ad hoc queries, but we also generate aggregates, which we write back to S3. We copy those to Redshift, and we visualize them with Tableau. And then that last line that's going from the Hadoop cluster up to that MySQL database, So that's our batch backfill for all of the aggregates that we calculate with Storm. And so we found that having a batch layer following up the real-time layer is really nice. It means I can take that Storm topology down for maintenance, and there won't be any repercussions. We'll always catch back up and have those metrics as the correct metrics. All right. So now I'm going to kind of talk about a bunch of kind of random problems that we've run into, that we've noticed, and that we've had to kind of come up with some solutions for. So the first one regards shards, buffers, and file sizes. So we quickly found out that those buffers in a Kinesis connector library application, there's a single buffer for every single shard, not for each instance of your application. So if you're running 35 shards on 5 machines, that means 35 buffers, not 5 buffers. And that could create a bit of a problem. If we wanted to chunk that data into fairly large files, like 128 megabyte files or something, we're going to run into some memory bottlenecks because those buffers are going to get fairly large, and our machine might not be able to handle all of that. At least, we're definitely going to run into memory problems way before we run into CPU problems if those buffer limits are set fairly high. So what's the obvious solution to that? Well, let's just make the buffers smaller, right? Let's output every 16 megabytes instead of 128 megabytes. And that definitely works. That means that we can utilize a lot more CPU before we run into memory problems, and we can run this application on fewer instances. But that creates a problem downstream for us, which is that Hadoop does not like lots of small files. And you can imagine if you want really small files, like 8 megabyte files, and you have, or maybe you're outputting stuff every 15 seconds. So each shard is generating 240 files every hour, and you have 35 shards. You're going to end up with 8 or 9,000 files every hour. And at our scale, that created some problems where we had to spend a decent amount of our clusters throughput in order to actually run our ETL jobs, just because of the overhead of setting up 8,000 map containers. And so that's what this is kind of representing. So we have a bunch of zip files sitting on S3. Our application master assigns one of those to every single, spins up 8,000 map containers and assigns one of those files to every one of those map containers. They go through, they initialize, they process the data really fast because there isn't very much of it, and then they output it to a reducer. And then they have to, we have to spin up another mapper after that. And yeah, that was definitely creating some problems. So our solution to this was we wrote a combined file input format. So we, instead of using the sort of default text input format, we wrote an input format that tells that application master to chunk all of those files and have multiple files read by a single map container. So it kind of iterates down the list until it gets to a certain file size, and then it tells that map container, you're going to process all of the data that's associated with this, with these files. And that was a massive improvement. So now instead of setting up 8,000 map containers, we set up 100 map containers, and now we use 30% of the resources. So instead of spending 20 minutes every hour running our ETL, we spend 8 minutes an hour or something like that. And that frees up a lot of time to do more ad hoc stuff. And if we ever get behind or whatever, it makes things a lot easier. It takes a lot of pressure off of our Hadoop cluster. All right, another challenge that we've run into. So the Kinesis API doesn't let you get the gateway IP address. There's no get gateway IP address method that you can call from a Kinesis record. And devices don't know their own gateway IP address. The only way to do that is to receive a message from the device. And so this was a big problem for us. We rely on IP addresses to do geo lookups, and geographic splits are really important for our platform. when we ran into this problem initially, we realized that unless we found a solution, we would not be able to use Kinesis because we need to know how much money we're making in each country. We need to know, how many installs we're getting in each country. We need to be able to compare the tutorial funnels across countries. We need to be able to limit analyses during beta to only beta countries, for example. It's really important for the sort of stuff that we do. And so this was a big problem. Fortunately, there's a pretty straightforward solution. We set up a web application. We had all of our devices upon session start, let's say, ping that web application. And that web application would then see what the IP address was. It could do a geo lookup, and it could return that data back to the device. And that was fairly straightforward to set up. And we thought it was working pretty well. But then we looked at the numbers a little bit. And for a lot of applications, we were getting like pretty good hit rates. Like we'd get 95% of the devices that we saw, 95% of installs we had a country for. But then for some applications, we were running into problems. These are sort of twofold. So first of all, it's mobile gaming. So there's a lot of people that will install your app and then like click on it to start, and then there'll be a loading screen, and then after 15 seconds, they'll run out of patience, and then they'll just be like, screw this, I'm deleting it. And so we were running into situations where we didn't actually have enough time for those users to send, for them to send us that event with all of that data before they exited the app. And granted, those are not exactly like high-value customers, obviously, but we are very interested in being able to tie all the way to the top of the funnel on a country basis. And then the second issue was we have a lot of different client teams. They want to make games. They don't want to instrument geo events. And so sometimes they would mess this up. And then we'd have to wait for an entirely new, we'd have to submit an entirely new build, like 2 weeks, 3 weeks later, to correct this problem. So right now, we're in the process of doing this, but we are switching out this architecture a little bit, and we're just going to have that web application act as a Kinesis producer and then send the data straight to Kinesis. That way, all the device has to do is ping a URL, and we'll get the data that we need. And then the other thing that we're doing with respect to this is we're testing out this very Amazonian sort of architecture. So we set up another version of this that uses the API gateway and has that call a Lambda function. And then the Lambda function does the geo lookup, or the Lambda function does the geo lookup and then sends the data to Kinesis. And this is nice because there's no hardware at all. There's nothing that you have to worry about at all. But we're trying to balance that convenience and lack of maintenance with the fact that this is a bit more expensive. And so our server engineering team is trying to figure out what they're going to do with respect to this. All right. So the last thing I'm going to talk about is scaling. So a question that anyone building a big data platform probably needs to ask themselves is, can our system scale with minimal effort and impact? So let's break this down. We have a couple different components, and how do those individually scale? So the stream, can we scale up and down with Amazon? Can we scale up and down a Kinesis stream? And yes, you can scale up and down a stream. You can split shards, and you can merge shards, which should theoretically cover all of that behavior. That can get complicated, though, and I'm going to talk about that on the next slide a little bit more. Can you scale up your consumers? You can always add more machines. If you quadruple your shard count, you can quadruple your consumers. And that scales up pretty seamlessly. Hadoop, same thing. You could always add more nodes. We're not super concerned about that. We have enough extra room right now. But if we quintupled our data or something, we definitely need to add more nodes, and that's something that's definitely feasible to do. And what about Storm? So I'll talk about some of the difficulties that we've run into with scaling up NStorm in 2 slides from now, after I talk about splitting shards. OK, so let's say you have 1 shard and you want to split it into 2 shards. That operation is pretty simple. You can call a split shard operation on your shard and give it the hash key that's halfway through the hash space of that shard, and it'll create 2 new shards, 2 new child shards. Really simple. All right, but what if you want to split those 2 shards into 3 shards now? If you wanted to split it into 4, you would just do this operation twice. Pretty simple. But if you want to split it into 3, it's a little bit more complicated. So you have to take your first shard, or in this case it's shard 2, and you have to split it 2/3 of the way down with the hash key that's 2/3 of the way through the key space, and that creates shards 4 and shard 6, which are of different sizes. And you have to do the same thing with shard 3 to create shard 7 and shard 5. So now you have 4 shards, 2 small ones and 2 big ones, and you have to merge those 2 small ones to create a shard 8, so that you have 3 shards that are of the same size and cover like contiguous ranges of the hash space. And so that's also probably manageable. But what if I want to take like 29 shards and then scale that to 37 shards or some? It's really nasty if you use prime numbers for this. It makes it much more complicated. That's going to be really difficult to do, and is going to involve like a lot of splitting with you're going to have to come up with a whole strategy for how to do that. It's not going to be particularly easy. So fortunately, someone at Amazon wrote this Kinesis scaling utils library. And so if you package that into a jar, all you have to do is give it the stream name and your new shard count. And there's sort of a deterministic way of doing this that's optimal, and it will go and execute that for you, which is incredibly nice. That being said, it's worthwhile to note that it goes a bit faster if you're doing a simpler sort of operation. So if you're going from 32 to 64, it'll run faster than if you're going from 29 to 37, for example. And scaling those things also sort of is like a little bit slower when your stream gets larger, because it can only do 1 operation at a time. When I think we scaled from 30 to 35, it took 30 or 40 minutes to do it. So this is definitely possible. Your Kinesis client library applications won't be affected by it, but it's also not the kind of thing that you want to do during like a highly critical time. All right, so what about Storm? So whenever we scaled up and down the stream, when we were first starting out, we ran into some issues, which is we couldn't refresh the list of shards. That zookeeper state, the state associated with our zookeeper prefix that was running, was hard-coded in there. We couldn't refresh that shard list. So what we had to do is we had to take down our topology, give it a new zookeeper prefix, and then restart it. And that's obviously problematic because A, we have to take down the topology, and B, we're actually going to lose some data because we have to default to latest. So there might be while we're doing that, there might be a couple-minute interval where we're like, we're going to lose out on that data, which could be problematic. It's not super bad in our instance, in our situation, but I can imagine situations where that would not be acceptable. Anyways, that issue was solved in Kinesis Storm Spout 1.1.1. Now all you have to do is a storm rebalance. So a rebalance will take all of the tasks and reassign them to different workers. So fortunately, that will repull the shard list, which means you'll be able to start processing data again properly, and you're still going to process every single tuple at least once. So that was like a major improvement. We're really happy about that. This is also something that you're inevitably going to have to do if you were to like add more workers. If you were to try to scale up and make your cluster bigger, you're also going to have to do a rebalance to tell your topology to take more workers. It's the same command. It'll automatically handle that zookeeper refresh, shard list refresh. One other thing to keep in mind is that empty records list backoff millis setting that I was talking about earlier, it needs to be adequately low. And the reason for this is if anyone's ever scaled up a Kinesis stream, after you scale it up, you have a bunch of closed shards, which are shards that have data on them that applications could read, but that aren't accepting new data. And if you have a topology that's running like right at the latest records, those are going to get cleaned out of data pretty quickly. And you're going to have a bunch of them, and so each of those executors, those threads, are going to end up with having to handle maybe like, let's say, 2 closed shards and an open shard. And like with the first version of the Kinesis storm spout that we were using, this was set to 500 milliseconds, and that created a big bottleneck because we would pull from a closed shard, get no records back, wait 500 milliseconds, pull from another closed shard, get no records back, wait 500 milliseconds, and then finally we were able to pull from our open shard. But setting that adequately low makes that less of a problem. So just make sure if you're scaling up shards and you have closed shards, that is low. Otherwise you'll run it, or that you have lots of threads, enough threads to cover all of your open and closed shards. All right, so that works pretty well, but there's sort of a side effect of this, which is that restarting or rebalancing causes tasks to lose their state. So this is sort of a weakness of Storm. It doesn't store any of the state, anything that needs to be kept in memory, any like lists of IDs or whatever it is that is being processed by a given task. And so when we would do this, we'd shut down the topology because we were scaling it up. We'd notice that like our daily active user count would all of a sudden spike. And it wasn't because we were getting lots of people showing up. It's because the list of IDs that we were comparing new IDs against was wiped away because we rebalanced the topology. So that breaks certain operations that sort of require long-running memory, like unique counts and joins. So maybe you want to store out attributes for a certain set of users for like a long period of time. That's also going to get wiped. So how do you deal with this situation? So our answer to this was to use Redis. So Redis is an in-memory key value store, and we realized we could use that to store a long-running state. So how do we do this? Well, Redis has some really nice data structures for handling the sort of problems that we were interested in. We could use Redis sets to count unique values, and we could do joins using key value hashes. And on top of that, easy deployment and management using Elastic Hash. So that's worked pretty well in our situation. And so what does this look like in practice? Well, on the left side over there, it's sort of part of a topology. Maybe you have a local aggregator that takes IDs from heartbeat events or something like that. It adds those to a Redis key, and then you have another bolt that is an aggregator that gets the cardinality of those sets and outputs it to somewhere. And similarly, that join topology, maybe you have 2 sources, and you have a join bolt that, depending on the situation, might do a hash map set or might do a hash map get, and then eventually output a joined tuple, which you might do some later processing on. And so I'm going to go through the simpler use case here, which is the unique topology. Show a really, really, really simple implementation of it. So 2 points of terminology to go over first. So the first is every single bolt, storm bolt, has to have an execute method. And that is the code that is actually called on the tuple when it enters the bolt. And then the second thing is there's this concept of tick tuples. So in addition to a bolt receiving tuples from some upstream node, it can also receive system-generated tuples every X number of seconds, and that's configurable by bolt. So in our situation, if it's not a tick tuple, we're going to add our item to the set. And you can see that just adds it to a list of IDs that's stored locally. And then if it is a tick tuple, so maybe that's every 10 seconds or something like that, we're going to call that emit method on that list of IDs. And so how's that going to work? Well, we're going to set up a Redis pipeline, and then we're going to iterate across all the IDs in the list of IDs, and we're going to add them to the set, sadd. Then we're going to sync the pipeline. That pipelining is pretty important, especially if you're trying to do something that's at fairly large scale. It means you don't have to query for all the responses from the Redis server after each event in order to proceed. It means you can just send a bunch of those things out and then collect all those responses later. And then that can eliminate a lot of network bottleneck. And then additionally, it's probably pretty useful, probably a pretty good idea to set some sort of expiration, especially for this sort of use case. We're trying to calculate daily active users. We don't care about this after the end of the day. We've gotten the total number. We can reclaim all that memory. And so that's that little Jedis.expire bit at the bottom. All right, so that's our local aggregator. So we implement that, and that's going to be able to that's going to send all of these records into a Redis set. And so now we want to get them out. And so this doesn't really need to be done with Storm. It doesn't rely on any downstream or on any upstream bolts. It's not this bolt is not actually receiving anything except for these tick tuples. The bottom little method is what you actually have to how you actually instrument a tick tuple. So emit frequency in seconds. You can replace that with whatever you want. This is just going to execute like every 10 seconds or so, let's say. All it's going to do is it's going to get the set cardinality from the key, and then it's going to emit it to wherever. So in our case, it's MySQL database, but it could really be wherever you wanted to emit it to. All right, so okay, so what did we talk about? We talked about the Kinesis connector library and how you can use that to build basic consumer applications really quickly. You just need to implement classes, or you just need to set up some classes that implement a few of those interfaces. It's really simple. How you can use the Kinesis Storm Spout to build to do real-time processing with Apache Storm. We talked about how you can get around some file size bottlenecks with a combined file input format. We talked about how you can do geo lookups with Kinesis in lieu of there being an API built into Kinesis that lets you get that information. And then lastly, we talked a little bit about storming, about scaling, and how you can scale up shards easily with that Kinesis scaling utils library, and about how you can manage that scaling with respect to your storm topology using Kinesis Storm Spout 1.1.1. All right. Thanks.